We did start the prayer a minute early.
So the plan today, do the homework quiz, just on continuity, like continuous at a point, continuous over a domain. We're going to look at we looked at one theorem in the last lesson about being able to push the limit inside of the composition. I had some strings attached to that. I'm going to show you some examples of like where those strings kind of come in and where you have to be careful doing that. And then we're just going to do some additional practice on ideally the squeeze theorem and intermediate value theorems. Do some extra practice there. And that's the plan. So not really moving forward, right? We're just going to kind of hover in place here for a minute. We're going to, like go through a couple of extra details on things that we've already talked about and do some practice on some of these big ideas that we've circled and seen an example or two on, but haven't had a chance to like settle in and really do some practice on. That's my plan. Everybody cool? Okay. So here we go. Probably do it twice.
Oh, you do the same? You do the same?
Hi, everybody. So, I want to start here by just looking at some fine points here on these two theorems that we mentioned yesterday. The one is that under certain conditions, I can push the limit inside of a composition. And then under certain conditions, if I compose two continuous things, the result is going to be continuous as well. Really the reason 9, that theorem 9, where if I compose two continuous things, under certain conditions, the result will be continuous as well is important to us. Is because if the function is continuous, that composition, I can just do a direct substitution, right? We saw that if you're continuous at a point, then the limit is equal to the function. So that's why that piece is up there. So this really becomes kind of my, the piece that I'm going to be using to tell whether I can push the limit inside the composition or not. It's just looking for continuity. And the most common way that somebody can throw a curveball at this limit of compositions type of problem is if they don't give you functions symbolically, but rather as graphs. So this is the place where you have to be pretty careful. So if I look at the limit as x approaches -2 of f of h of x, we're kind of hoping that we can say, well, that's just going to be the f of the limit x goes to -2 of h of x. And if that's the case, I can just go to my graph of h of x. I locate -2. So that limit should be 1. Is everybody okay there? And then if I do f of 1, I find 1 and I plug in. So it looks like at 1, f of 1 is 1. Now the thing that I'm checking is to make sure that f is continuous at x equals 1. As long as I have that, you can plug in, it's a no-brainer. So these equal signs I put a question mark over, it's okay. And the way I'm confirming that is that I have f continuous at that inside piece. Is everybody okay there? Okay. Let's look at another example. So here it's we're given a new f and h. The limit as x approaches 0 of f of h of x. So again, we're going to try to push the limit inside. So I go locate 0, and for h of x, what do we notice? We have a discontinuity there. So what's the limit as x approaches 0 for h of x going to be? Does not exist. So if that doesn't exist, can I do the limit of the whole composition? No, still does not exist, right? Okay. So again, the discontinuities are the places where I have to be careful on this. Marcelino?
Is it do not exist if the first function works and I plug it back in, it doesn't work, and there's discontinuity?
That'll also be and that's going to be, I think, the next example. And actually, I should say sometimes on yours, not all the time though. It depends on what the first graph looks like, which is rough. We'll see it. I'll do some example at the end of that. So again, same idea. So okay, well, I have a limit of a composition. I'm going to hope that I can just push that limit inside. So if I look at -3 on h of x, the limit there is fine though, right? That looks like it's +3. If I locate 3 in G, We're continuous there, so we're good. Everybody's okay? So again, the idea here is we had a discontinuity in the inner part that caused the limit not to exist. We have a discontinuity on the inner part, but this time it was fine, right? Because the limit still existed at that discontinuity. So just looking for the discontinuity on its own is not enough to say it doesn't exist. Is everybody okay?
So there is a wall on it, you can still count it, like for G of 3, like it doesn't matter.
Doesn't get in the way because we're not plugging into H. We're taking the limit at H,
Okay.
right? And that's why it doesn't matter, the whole.
If you did plug it into H, then that would be an issue. Or like if H was like.
Potentially,
Yeah.
yes. Potentially, yes. Let's do another. Again, start the same way. So if I look at g of x at -1, what do you notice here? So again, the limit does not exist, so it doesn't matter what you're doing afterwards, right? I can't take f of does not exist. That just doesn't make any kind of sense, so that's going to fail. So let's take a look at, oh no, you came back without a computer.
Yeah, they said it was going to take a lot longer, so I said I just.
Okay. Let's look at these couple. So here's the limit as x approaches 0 of f of x. I'm going to be plugging it into itself. Everybody's okay? That's why I only have one graph. So we'll start the same way. So if I locate 0, f of x is 2. But I'm plugging here into a discontinuity, right? Can I make a direct substitution into a discontinuity? But this does have an answer. And you do have enough here to get the answer. Here's the subtle part. This limit as x approaches 0 of f of x, it's approaching the y-coordinate of 2, but it's always approaching that y-coordinate of 2 from below. And it's coming in from below. So this becomes, then, rather than this, we can say it's the limit as x approaches 2 from below, or from the left, of f of x. And that we can do. Now, hold on to this for a second, because what we just did was subtle, right? This was tricky. Let's look at this again, okay? So I'm going to just go off to the side here and kind of write some more. So if you have a question about what we just did, is that what Adrian? Yeah, let's talk about it a little bit more, and we'll go back and circle back and re-explain after we talk about a little more what's going on with a composition, okay? So if we have just some composition, f of g of x, right? What's going on is you have some x value, you apply the function g to it to get some y value, g of x, right? Or this is like an input and this is an output, right? Then we take this output, which now becomes my input, plug it into F, and get a new y coordinate, f of x, right? Or I should say f of g of x. That's kind of what we're doing with a composition as far as inputs and outputs go. Does that look familiar? Okay. So this piece essentially in our limit discussion becomes like the limit as x goes to g of x of f of x. Right? So the taking of my g of x and plugging it into f in a limit discussion is the same thing as just taking the limit as x goes to g of x, whatever that number is, of f of x. So what we did here was my inner function was going to -2, or sorry, going to +2 from below, right? Because it's a maximum. So I can rewrite this limit of a composition as the limit as x goes to that maximum value from below, because the graph is always less than -2 in the neighborhood, I'm sorry, less than 2 in the neighborhood of 2 of f of x. And that we can evaluate. Let's do another. Yeah? Lucas? So yeah, if it was, let's look at this example. So we're doing the same thing, right? So this is your question. So again, we think, okay, do this. And again, this is 2. But at 2 we have, so we're not sure what to do, right? If I go back and look at this though, how is f of x approaching 2? Well, it approaches both from above and below. What can I do with that? I have, which end should I look at? Well, they're different, right? This guy is going to be, just does not exist. So you can't even look at f of 2. Now if I had something that did so let's say we have this, and we're doing that same problem. Notice that this time we're approaching 2 from above, right? So we can rewrite this as the limit as x approaches 2 from above of f of x, which would be going to this value. I don't know, let's say it's 4 or something. So Lucas, your question is, it matters whether we're approaching that value from above or below, in as much as it tells you which end of the jump discontinuity you need to be looking at to do the limit. And if it's approaching from both directions, there's nothing you can do with it. It just does not exist.
Okay, so when it's approaching from above, look at it. That's just going to
Oh my goodness. Yeah, did I have this reversed back? This is what you were barking at me about. I was looking at the wrong end, right? No, that's right. 2 from below. Oh, yes. I see. No, 2 from above. That's 2 from above, right? Those are the values bigger than 2. Can you repeat your question? I think I misunderstood what you're asking. Because I said some stuff and now you're looking at me like, what's going on?
Yeah.
Let's start with you, and then Anthony will go.
Okay, so I was asking a confirmation question. You're saying, so
Yes.
it comes from above, so I mean, the limit is going to 2 from the right, but from above. So then you would look at the next function as it goes to the limit from the right, because it's the other one is from the
Yes. And so above really means minimum, and below really means maximum. That's what we wanted, right? So like translation into super specific. Yes. That is accurate. Can say Anthony. Oh, yeah. Yes. Thank you. Adrian.
I was just gonna ask, I think we might want to do this, but like, would you still write X, even if we're looking at, like, it's going to the 2 on the y-axis?
So, but remember that, so when we look at our composition picture right here, that g of x is the output of the inner function, but now is the input of the outer function. So this y-coordinate of 2 is the x-coordinate for that f. So that's why we still are using an x here.
So then how do you know the difference if it's actually like, if it's like going towards 2 on the x?
Okay.
The function.
Yeah, so when you say it, are you talking about the inner or the outer? Okay. So the inner is going to 0, and that limit is like 2, right? That now becomes the x value for the outer function. So this is like the limit as x goes to 2 of the outer. They get it? Okay. Maybe this was a bad example to use f onto itself, because normally we have f and g's and then it's a little bit clearer, like which one is the inner and the outer. So, like this is outer, inner, and this is then outer, right? Or if I add here, this is outer, this is inner, and then that's outer.
I guess what I'm saying is why we don't switch. Like, you say X the whole time, even though you switch, like after you switch to the outer, you still say that's X.
Right. So, I mean,
even though it's like approaching the bottom.
yes, but remember this is a Y as it outputs from G, but then it becomes an X when you put it into F. Right? When we talk about f of g of x, like plug an x in, a y comes out of g, that y then becomes the x for the outer. Right?
Yeah. So
that's why it's just x all the way through. Even though it was a y coordinate for the inner function, it's now the x coordinate for the outer function. Is that?
Yeah.
So that's, again, like, ugh. But This is the takeaway. This right here. That's the piece that you really need. Okay? That's the part that you, that's Lucas did a nice job of like nailing down like, this is what do I actually need from this? This is the piece. And this is really the only way or the only circumstance that I've seen when like looking at hundreds of AP questions where you can get in trouble pushing a limit inside of a composition. Because the only kind of situation where you need to be careful is where you have the two functions defined as graphs, and you have like the inner function is hitting a max or a minimum, and the outer function is a discontinuous. If that doesn't happen, everything just works as you'd expect. Nothing weird happens. This is the only place where it's like, how did you get that? Where I had to sit there and look at it, and be like, now I got it. That's a subtle Lucas. Correct. Yes. If you're given like your functions are defined as like equations, I think you're good. I've never seen a situation where you can't just like push the limit on through and have it not work out for you. Unless it like pushing the limit through makes like some indeterminate form or something. But otherwise, like go ahead. You should be feel okay? So the other piece that I wanted to do today is just some general practice. So I have a delta math made up that has a couple of different types of questions on things we've been working on recently. So I want to start with the squeeze theorem one. And this is majority of the time, this is going to be the presentation of like a squeeze theorem problem. Where you're given that the inequality exists. You're given the upper bound, you're given the lower bound. You just need to evaluate the limit of the thing in the middle. So for the squeeze theorem, what do I need in order to do this? So I have that string of inequalities, that's what I need, right? And then the limit of the upper function and the limit of the lower function, if they're equal, that tells me that the inner function has that same limit. If they're not equal, it tells me nothing. Doesn't tell me the limit doesn't exist, doesn't tell me what the limit is, doesn't tell me anything. So you just can't say anything more about it. That's why you have the cannot be determined option here at the bottom. So all we're really checking is the limit as the limit of 18x minus 19 as x approaches 2, and the limit of blah, blah, blah as x approaches 2. Notice both of those functions are polynomial. So to do the limit, all I have to do is direct substitution in. Easy, right? Very simple. You just have to know what you're looking at. So if I plug 2 into this, I get 36 minus 19, so 17. And then I have 20 minus 4, that's 16 plus 1, 17. So they both matched. And I'm good. If they don't match, you just say cannot be determined. Well, the squeeze theorem only applies if the two limits, or the limit of the upper and the limit of the lower, are equal. If they match, then you can use the squeeze theorem to say the limit of the inner function is the same. If they don't match, the squeeze theorem doesn't apply because it doesn't meet the conditions you need in order to use it. So you can't say anything about that limit.
So the way we just did it now was plug them in. Last time we had like a sine or we had a cosine. Why were you doing stuff to like to the inequality?
So in the example we did in class, we weren't given this. We weren't given a function for the upper or a function for the lower. So I had to build my own. Here, you had the inequality. You had the two functions on top and bottom. You don't need anything else. You don't have to build your own functions at all to use. They gave you the functions to use. You just had to use them. So they gave you, here's the string of inequalities. Those are the functions on the top and bottom. You just had to check the second condition is that the limits were equal. When we did the example in class, I didn't have anything. I just had to do this limit. It was indeterminate. I couldn't algebra my way through it. So what did I do? Well, I built my squeeze theorem situation. Okay.
So most of the time we will be given the full equality.
Yeah, this is the most common presentation for a problem like this. It's like you have the stuff that you need to do it. You just need to check that those two limits are equal or not. Everybody's okay? That should be okay, right? Relatively straightforward on what to do with that. And again, the limits, these limits, or I should say these limits, those should be easy, right? They'll be like just stuff you can direct substitute in, more than likely. The thing we talked about at the end of class yesterday was this intermediate value theorem. This was the other big theorem from this first block of stuff that we're going to do that is like a memorization theorem. Much like the squeeze theorem, you need to know what the initial conditions are and what the conclusion is of it. You really state those kind of things in words. So like on the previous problem, you can say since, like f of x, or g of x is less than f of x is less than h of x, and limit of, f of, or g of x was 17 and h of x is 17. The squeeze theorem states the limit of f of x is 7. Like you list that it meets the conditions and you list the conclusion and quote the theorem name, and that's enough. You have to it doesn't have to be word for word, but like you have to show that I've demonstrated that the conditions are met, even if it's just restating givens, and then the conclusion and the reason why is just the theorem. So the other one that we need to be able to do that with is the intermediate value theorem. So this is an example, and I really like this example because like what this is doing is it's kind of like giving a template of like how to answer this question using the language of the intermediate value theorem. So it says the function f of x is continuous on its domain of -9 to 9. And is plotted below such that the portion of the graph on the interval from -6 to 1 is hidden from view. Given that f of -6 is 4 and f of 1 is 6, determine what conclusions can be drawn from the intermediate value theorem on the interval -6 to 1. So the conditions for the intermediate value theorem are that f is continuous, and that the y coordinate that you're looking for, you have a y value below and a y value above. So we'll say, since the function is continuous, the intermediate value theorem can be applied. And since it can be applied, now we have some like filling in of a template to do. Okay? And it states for any k, that's our y coordinate, in the interval from, well, our blank here in question, the y's go from 1, 2, 3, 4 to 5, 6. So I'll say from 4 to 6. Where did my things go? There exists a C, that's an X, where C is between -6 to 1. Such that f of c is equal to k. So then it asks, must there exist a value of c in the interval from -6 to 1 where f of c is equal to 5? Well, is 5 in between 4 and 6? So yes, there has to be some c along the way where the x, an x value in between where the y value is found. Lucas. Well, if this is not continuous, he doesn't say anything about whether that could be or could not be. So if you have something that's outside of the y's, right? If you are looking for a y value down here, well, that's not going to happen, right? So I think that's probably all it wants, but let's do another, right? So what's the nice part about this? Again, it's giving you the template. If you have to apply the intermediate value theorem, it's like, here's the language, and this part of the language is the same every single time. These are the parts that you fill in that are specific to a specific problem. But like, otherwise the language is all the same. Isn't that really nice? Like a nice way to practice this? To think about it like a template? Let's do it. Again, it says the function f of x is continuous on the domain -9 to 9 and plotted below such that the portion of the graph on the interval from -3 to 3 is hidden from view. Given that f of -3 is 4, so that's the point -3, 4, and f of 3 is 6, that's the point 3, 6, determine what conclusions can be drawn based on the intermediate value theorem on the interval from -3 to 3. So again, the function is continuous. So the intermediate value theorem can be applied. So any k that's between the y coordinates of 4 and 6 need to like staple this to my face or something. There exists a c between x's, -3 and +3. Such that f of c is equal to k. Must there exist a value c on the interval where interval -3 to 3 where f of c is equal to 2? So does 2 fit in between these? No. So I don't know that it's possible that it goes like whoop, like down and then connects if it's continuous all the way through. It's still possible, but it doesn't mean that there must. So I would say this one. Let's see what it says on that. Yep. So again, it's possible that I could draw a graph where this like goes down, but it doesn't have to. It could just like go from there to there. So I don't know that 2 is possible, but it could be. Not guaranteed to have it though. Do you guys feel okay on doing this? You see how this will be useful practice as like a scaffolding on what to do. This kind of practice should look familiar, right? What does this look like? The homework quiz we just did, right? So to check if a piecewise function is continuous at a point, you need to look at left-hand limit equal to right-hand limit equal to the function being evaluated there. Everybody okay? So all I'm going to do, I'm going to plug 5 in. When I do that, I get negative 21. Plug 5 in. When I do that, I get negative 24. Are those the same? Tells me the limit doesn't exist, so it can't be continuous there. Done. Hey.
Would we do the zero process for proving that at a point, or is that just putting it at the number?
Yeah, same process for proving the point.
Okay, so it means the same thing.
So we're not proving the function is continuous. We're just proving it's continuous at the point x equals 3.
So when I export continuous over like the whole thing.
Yeah, so to do that, you have 2 extra steps that you do. So you still need what we just did, but you need to say that, like, for x less than negative 3, we're continuous because it's a polynomial. And for x greater than negative 3, it's continuous because it's a polynomial. And at x equals negative 3, it's continuous or not because of, and then the check. So it's just like, you just got to remember to state, because more likely than not, we saw in the notes yesterday that every single function that you've encountered is continuous over its domain. So like the pieces you're going to get to make this piecewise function are going to be things that are continuous over their domain. The only thing you have to worry about is like, do I have a rational function that's like a vertical asymptote somewhere in here or something silly like that? And I wouldn't say that I'm not so sneaky that I wouldn't do something like that to you, but I think that'd be awfully sneaky. Is that feel good?
Yeah.
Okay. So like again, the difference between continuous, like a piecewise continuous at a point, and continuous over the whole function, very good. Right? You just have to say 2 other things. You don't have to write, you don't have to do any more math. You just have to say it. And that's it. So we said this one. So if we do this, I have 9 times 5, that's negative 45. And then minus 18 is negative 37, I think. And then we have plus 6, that's negative 24. But you know what? I didn't even need to bother checking the limits. I could look at this and tell it's not continuous already. Because f of negative 3 isn't defined. So it doesn't even matter what the arithmetic is. Knew it wasn't continuous already because f of 3 didn't exist. So if I look here, f of 4 exists, and it's going to be the same as the right-hand limit. So really, we just got to check the right and left limit and make sure they're equal. I can do both those checks with direct substitution. So if I'm plugging 4 in, I get 11 minus 32, so negative 21. And if I plug the 4 in, I have 11 minus 8. It's not the same. And you guys get the idea, right? So again, just like some extra practice, get you quick feedback. Oh, let's do this one. This is another very common presentation. So this reeks of AP multiple choice question because it's like find the value of k, and that's an easy thing. So this is a multiple choice question. So it says find all the values of k that would make this function continuous at x equals negative 1. So what I need then is I need this k to fill in the hole in this rational function, right? So I'm just going to solve, or take this rational function, I'll reduce it, and then plug the -1 in, and whatever that number is, it's got to be what k has to be in order to fill in the hole that would be our removable. So looking at this, that's going to be x plus 4 over x plus 1 when I reduce it. If I plug -1 in, that's going to be well, that's going to give me a vertical asymptote at -1. That was, I don't think that there's a solution to that. Okay. I was like, wait a minute. That didn't work out at all. And I'm like, oh, that's why. So you canceled it out. You have the hole there, but that doesn't matter. You have a vertical asymptote here. You can't fill a vertical asymptote with a k, or just like a constant value. So you can't do anything. Great. Perfect. This is even better. So for this to be continuous, I need the limit as f of x, or limit as x approaches 2 from above of f of x to be k times 2 squared. And the limit as x approaches 2 from below of f of x to be 2k plus 4. I set those two things equal, and then solve for k. It's a quadratic there. And now I can't do it in my head anymore because I've already lost what the values were, but you get the idea, right? Worst case scenario, you might have to drag out the quadratic formula there, but it's probably factorable. Well, this one has a nasty leading coefficient of 4, so maybe you would drag out the quadratic rather than factor it, because you got to do that long factoring because of the leading coefficient. But whatever, right? It's not so bad. You guys feel okay on doing this kind of thing? And this is very, very common multiple choice question presentation. Almost like when somebody's writing your test, they might include a multiple choice question in a similar format because it feels like a really good one. Just throwing that out there. It's lovely because you can do it with or without a calculator, so it doesn't really matter what section I put it in because the math is, like solve a quadratic level math, which should be doable with no calculator. So this next one says use the definition of continuity to determine whether the function graph below is continuous at x equals 3. So if I look at x equals 3, continuous there? No, right? Because we have the whole. What did I just do? Oh, I lost that. So what do we have here? The limit from the left is 3. The limit from the right is 3. And it can be determined that the limit exists and is equal to 3. Furthermore, this is undefined. Therefore, it's stated the function f of x is not continuous at 3 because the limit exists but is not equal to the function. Oh, did I pick the wrong one? Oh, okay, whatever. But it's still not equal, guys. But it still said that was wrong. What did it say? What was wrong with that? Did I pick what? Oh. Yes. Duh. 5. Okay, so I made the stupidest mistake possible. But you get the idea. Again, what do I like about this? The format where it's creating a scaffold for like you to prove using the definition of continuity that a function is discontinuous, right? So like it's creating the language to get you better at writing these answers. Is that, you see why I'm picking some of these things? And then last type of problem, it says the graph of the function f of x is shown below. State all values of x on the interval, blah, 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 for which the function has a jump discontinuity. So if you look at that, -4 to 6. There's not much to say about this other than like it gets us practicing at the vocab. That's not what I meant to press. About what the different discontinuities are. I assume that you'll get other things, so just generally discontinuous. We'll probably have holes. We'll probably say infinite discontinuity or vertical asymptote. Those mean the same thing. So just kind of helps practice what those things are going to look like. How do you guys feel? Any better about what we've been doing? You know, you came in and told me that you didn't feel good about stuff.
Yeah, I think that.
Are you sure? Okay. We have what, like 15 minutes or so. Why don't you guys open up the Delta Math and do some practice on this? Whatever felt like this is the thing I want to work on right now because it feels precious for me, but that's the thing that's going to be hard for me. Try doing that. Yes, go ahead. What's up? Yeah, go ahead. I think she's going to do it. But go ahead.
I really don't want
Oh!
I know everything.
Yeah, you have questions on
It's only 20.
There's Dan, it's time right now to talk about it. Do that?
Yeah. And now they come
So this is going to be an intermediate value question. So what I would do is I'm going to subtract everything on one side. So it's equal to 0.
all that.
So now we're going to find an x, it's a negative, and x is going to be If I do that, then I know that somewhere in between those, the graph crosses.
Oh, yeah.
So if I get like 0,
Yeah.
that's negative. And then if I get like pi, positive, minus 0, or I'm sorry,
Like I just dropped down
But still, that's gonna be positive. So we've gone from negative to positive, somewhere between there.
That's really sad.
And then it says find, use your calculator to find it. Oh, then yeah, wow. Oh. Does that make sense? Yeah, identifying like, anytime you're proving that like something exists,
I don't think so.
it's almost always like a field and physics class, like proving that a graph has some specific y coordinate. So I'm just learning that. Almost always. Yeah, you just have to find, so this is your thing, that's zero, you just have to find an x is negative and x is positive. It's somewhere in between there, across the zero.
And I'll just say that using the intermediate.
You do need to say that it's a continuous function, but
Yeah, you should.
it's a continuous function minus continuous function. So it is continuous, so like, that's all you need to say. You do need to make sure you say it.
I know, she was behind us.
So two things you need to find.
That's how much
Continuous. And then you have to find, the upper moles. Yeah, that's okay. I feel like part of it is just like to get you to like, or just like. And like some of the things
With the small or big things.
that's okay. That's okay. And some of these that
I know everything. You remember last time?
That's a really and I know you don't worry. We should have done because there's just like all that part of like building up some intuition and it's always going to be like a little behind. This was easy when I look back at it.
There's no it's doing the 7th, bro. If there's a whole delta analytical delta yeah, number 2 analytical I know, but I'm like,
There's a hole that
I don't know. I asked for letters or I'm like,
So it's not asking for something specific. It wants you to use the definition of
the smaller one has time. I'm like, I don't know why you hear that.
So you literally just write the limit as x approaches 4. That was x equals f. That's all it is. It doesn't want something specific.
But I tried to set them equal to each other. But it's like, I don't like
It just wants you to use the definition of a function.
it was like fun. I asked her
yellow, and I'm like,
wait.
You read that, and I understand what you were saying.
Overall, it was fun. Like I said, it's like, oh my god! I know! I think she got like why would I'm not?
Same thing. Not for that.
That's the first time.
Yeah.
Honestly, yes, not like so much time.
That's confusing, they're the same page.
Yeah, it's the exact same thing.
I wish I would have gone like the.
It's just 'cause
like
if I don't,
that's what was like insensitive. Like,
if I don't specificize it, then it's less different copies than I
but I didn't get
know.
my.
Like, you'll recognize it.
I was making sure.
I got it. It's like balances liability, equity,
Cortisol.
I got bed.
And then it just turned this to like, yeah.
No.
Yes.
Oh, no, it's
Or if you couldn't see the pattern, just by that.
Yeah, so then I'm like, I look awful.
You can't mess up because it's not clear
Yeah.
red and left.
Because then I'm just
It's
being
the right. It's
I got my hair done right
Oh, where the body is.
I literally got my hair done.
This thing.
Yeah, it's all down.
Is it like, is it just another result? Is it like, so is it a one-time
It's, yeah, so it's they're semester different.
Oh.
Semester one is mostly like a higher situation where it's like a single. And then other situations. So I actually ran past semester one, this is my first experience. That's
Yeah, I don't know why. I'm really good. I'm so glad that SEC is like, no, I don't think so much. Yeah. Well, this is the first time that it's all like, yeah, and I did turn my head right. But since,
Like that's bad. I'm gonna wake up and
but maybe it's the first time doing it, so maybe it will be kind of like in our favor. I feel like, you know what I mean? But if it's not, you know, it's high power. Yeah. But also, yeah, especially if they're like, we're trying to make it like something very of course they would want me to see this. The thing is, like, I don't know how, but I'm like really good at science, and like, I think okay, like, I'm like, yeah. What do you have right now?
They are.
Yeah.
So it would be like,
Like shaking and everything. Yeah. My super score, if I got any of my scores on 150, so like all I need is just bring up one place. Now my super score, I think it's only like 2 points. That's it, and more. So like, I know, but I have to just like, I studied all last summer.
Oh, yeah.
The beginning of June. So know is that I'm not now like yeah, I know. Yeah, I'm just wanting to see it go down.
Yeah, that's all. That's all. Just if you do it right.
Some people
Sure.
But you're not going to. Oh, I thought he was like, oh, yeah.
Make it bigger.
Okay, yeah, my bad.
She's not. She's the most unreasonable person.
Yeah. I think I know, I got up last night, I got over my eyes, I kept
Yeah, okay. Because we know that for those little
I practically did it in my bed. Yeah. Like, we're gonna be like, oh, no, I don't care. Like, I was like, it's my person.
You're welcome. Have a good day.
I don't know.
I'm trying to ski, but I'm like, I'm really
I saw looking at it. I did it. I think I did it right, but for some reason, instead of writing, instead of writing like limit.